Well, welcome to the afternoon session. I believe the last.
I think you need real lung power. Would you please sit down? Go ahead.
Okay. Welcome to the last session of the summary talks. Our team has focused on the problem of joint processing of audio and visual information. If you actually think about the progress that we've made in speech recognition, it's actually obvious that one of the key challenges has been where want to have really reasonable large vocabulary systems running in natural environments. And the challenge there is our ability to actually have a knowledge of what environment that we're going to run in. In other words, if you actually train the systems in particular environments and you go to a completely mismatched environment, either due to noise or you train on one telephone channel and you actually test on speakerphones, the recognition systems degrade dramatically. And in spite of a large amount of effort in this area, we still have not made substantial indents in making this progress in this area. So one of the motivators for me and for us here on the team was to answer the following question. How do you exploit visual realization of speech to improve audio-based recognition, in particular to mitigate the limitations of audio-based recognition in conditions of mismatch? Although the focus really has been in getting improvements in the mismatch conditions, especially due to noise or channel, the ideal goal would be to see if we can actually improve recognition in clean environments as well. Most large vocabulary systems seem to have roughly saturated. If it's at between 5 and 10% error rates, can we actually get improvements in clean conditions even better than that? So before I go into some of the different aspects of the system, I just want to point out a few things about the team members that are worth noting at this point. I want to say Marcus Potamianos has spent great amount of effort before the workshop to actually have all the data ready for the workshop, which took a lot of full nights on his part to get it to a stage where we could do reasonable experimentation during the workshop. The second thing is Juergen Luettin has been extremely critical in setting up the HTK environment for us to be able to do experiments in the first couple of weeks. It took us almost the first couple of weeks to actually get a decent matched numbers relative to our IBM numbers. Iain Matthews, even before the workshop, his processing, which we'll go into a little detail later, requires a lot of annotation of data, and he had some of his undergrads at CMU help him, along with the undergraduate students here, June, Sison, and Azad, who helped in the first couple of weeks to get some data sets going. Dimitra, again, joined us a little late into the workshop. However, I think she has made incredible progress during that time. Herve Glotin is classically known as the guy who doesn't sleep at all, and he's worked really hard to get to where he is now. Of course, and Jie Zhou has helped us not only in some of the experiments that you're going to see here, but also in the data collection on the CNN data. With that, I will briefly tell you what the various parts of the system are. In an audio-based system, what you have is, we actually, in audiovisual speech recognition, we are starting with a camera that, and a microphone that captures simultaneously the audio and the visual signal of a speaker speaking in front of the camera. We actually digitize that into compressed form, typically MPEG-2, to trade off between good compression rates and quality. We demux that to get the audio signal, decode it, decompress it, extract audio features, generate an acoustic model, and then this typically combined with a language model and a search algorithm produces a word hypothesis. Now, what is different in when you do visual speech recognition, audio-visual speech recognition? What you have to do is actually decode the video signal, and in addition, a piece which does not really exist in audio-based processing is extract the region of interest, which is what the region of interest is not really clear at this point. We have, for our baseline experiments, assumed that the mouth region, rectangular box around the mouth region, is our region of interest. Iain Matthews is going to talk about an alternate approach which actually represents the whole face. Once we have the region of interest, we represent this in terms of visual features. Although for acoustics, capsular features have become sort of the de facto standard in representation, it's not really clear what the appropriate visual features are that encode the information that we want from the visual signal. You'll see some aspects of that modeling a little later. Finally, coming up with the statistical visual models, here again, the issues are not clear in terms of what the right unit as against the acoustic phonetic unit that we use in speech recognition. Once we have this, the challenge is to combine them in ways that will allow us to give a joint performance that is better than either stream, in particular in our case, audio-based recognition. In this particular workshop, the methodology that we have actually adapted is where we have generated what are called word lattices. This is really a lattice of all the possible hypotheses at various depths coming from the acoustic recognizer, and we have rescored these lattices using various kinds of models, whether it's visual, various kinds of combinations. So to reiterate, the key research issues in any research direction of this sort is the first thing is data. You have to have a sizable corpus from which you can actually train and test your results. And this really has been a challenge in audiovisual speech recognition. Most of the previous efforts were really focused on very simple digit or alpha tasks, in particular either isolated or connected at best. And our goal here was actually to move from that kind of a domain to large vocabulary continuous speech recognition using subphonetic models as against the word models that are used in the other processes. The second, once we have data, as I said earlier, locating and tracking the region of interest is a non-trivial problem. It's still a challenge, and for this purpose of this workshop, we've used some code from Andrew Senior at IBM to actually able to do that. Iain has a slightly alternate approach, which he's going to talk about later. Then the second is specification and representation. Here we've actually, in this workshop, focused on so-called discriminant feature representations. Given the knowledge of the class of interest, can you come up with a representation of the stream of interest in a way that discriminates best amongst the classes? Marcus is going to focus on it. Active appearance models is this alternate scheme where not only do you look at the texture of the region of interest, but you're also encoding shape characteristics as well. The other stream or thread that we're focused on is, can we come up with better visual models? In other words, are there ways to encapture visual equivalence classes and based on the fact that there are fewer vicemes, these are visually distinct phonemes, than acoustic phonetics to do the models better. And June and Azad are going to talk about that. Visual model adaptation, this is a simple case where we said if we adapt the visual characteristics of the speaker on a per speaker basis, do we see improvements just like we do in acoustic speech recognition. And the primary focus to a large extent has been on fusion strategies, where we've looked at several different kinds of strategies. One based on feature-based fusion, other based on different levels of synchrony, and I'll talk about that a little, synchrony and asynchrony, and finally places where you actually weight the two streams at the unit level rather than at the entire utterance or a global level. So the key challenge from a mathematical point of view is really to come up with nice models of this joint distribution. In this, it's a very slightly general representation where there are S observation streams and you are given some class of interest. In this case, it could be a phone or a word, and the idea is to come up with this joint representation and model that in a nice way. And the way you model this will really depend upon what kinds of assumptions you can make about the two streams, whether they are dependent or independent. If they are dependent, you would actually model this as a single process, generative process, where a phone or a word is generating the joint observations simultaneously. If they are completely independent, you would make independent decisions based on these two, get the individual distributions, and the final sort of measure of what this joint distribution is a function of those individual distributions. And also the second thing is asynchrony between streams. There are two reasons why this is important. One, there is evidence to suggest that, especially at the onset of speech, the visual production or visual articulation of speech precedes the audio production. The second thing is, when you actually encode this data into some digital form, typically there is a lag between the audio and video of about one video frame. The levels at which you can assume asynchrony, again, is an open research area. In other words, do you say that the asynchrony is at the phone level, the word level, or the utterance level? What I mean by synchronization, the feature is really the feature fusion, where you concatenate the feature and then have a single model. In the classes of interest, when you are combining, you think about visual classes of interest or acoustic classes of interest. On the one hand, you're looking at acoustic phonetic speech recognition, and you're augmenting the visual information. So you may want to look at phones. On the other hand, the only discriminable information in the visual stream is based on the visemes. So what is the right class of interest? And finally, it's very important to think about some measures of reliability of the two individual streams, which weight the relative strength of the combination of these two streams. And there are different ways to think of it. Signal-based approaches, where you actually have estimates of SNR. Herve is going to talk about an interesting way to measure actually voicing using a harmonicity index. And entropy is something that Iain Matthews has tried before. We haven't done anything in this workshop. So before I turn it over to the other speakers, let me tell you some basic facts about the data. Marcus is going to expand on this a little more. So what we did at the very outset, the clean data, which contains 261 speakers and 35 hours of training, 26 speakers and 2.5 hours of test, vocabulary of 10,000 words or so. The clean result is about 14%. And the first couple of weeks, as I said earlier, was spent in making sure that the HTK matched our IBM results. On this set, the oracle error rate, where if you knew the truth and you found the best path that corresponded to the truth, is about 4.5%. So in principle, the room for improvement is as much as this, given you have some method to do so. And we also did this based on Sanjeev's suggestion, this notion of a random path through the lattice. This also gives a measure of, if you had no information, how would you do? And this on the clean lattice is about 45%. So we are doing quite well. There is enough information in the acoustics here. Similarly, at the 10 dB speech noise, again, the HTK and the IBM baselines differ slightly. This is the match in the exact language model weights, but they're roughly similar. The oracle error rate here is about 27%. So we could, in principle, have improved all the way down here. And then the random path through here is about 78%. So with that, let me turn over the presentation to Marcus, who is going to talk more detail about the databases and the front-end representations.
So at the beginning, I will speak a little bit about our database, and I will continue about the discriminant visual front end. So the audiovisual database. So this is the IBM Via Voice audiovisual dataset has been being collected on and off for the last 1.5 years. Mostly about more than half of this set has been collected over the last actually 2 months before the workshop, using an automated system that Giri and Gar has developed at IBM. The current state of this dataset, it has 290 subjects. It contains 50 hours of a large vocabulary audiovisual continuous speech set. The vocabulary size is 10.5 words. The subjects are recorded on frontal face color video. The resolution is 704 by 480 pixels. The frame rate is 30 Hertz, and it's MPEG-2 encoded of a rate of about 2 gigabytes per hour. So this is about a coding ratio of about 40:1. The audio is 16 kilohertz, and the recording conditions are clean, sort of typical, semi-clean, let's say, typical office environment. So these are just some examples of the speakers, and you see more or less their aspect ratio with concern to the frame are pretty standard, and there are various, I guess, variabilities between the speakers, for example, glasses, etc., beards, mustaches. I mean, we have a lot of speakers like that as well. In terms of the experimental setting, we have split our data, which is about 50 hours, as we said, into, first of all, a speaker-independent data partitioning. So we have 35 hours of training. This is about 17,000 utterances. Then we have about a 5-hour held-out data set, a 2-hour test set, and in addition, we have an 1-hour speaker-independent adaptation set, and G is going to be reporting experiments on that set here. Furthermore, we had also another split into a multi-speaker held out and test set, just because we were not completely sure whether the visual front end was going to carry out similarly well between the multi-speaker and the speaker-independent sets. As far as the audio is concerned, we're going to be reporting on 2 experiments. The first one is using the original audio, which is clean. And the second one are going to be matched noisy experiments, where we have additional bubble noise added to the audio signal. And the SNR of this experiment is about 10 dB. And all the models that are reported there are much trained on the same practically audio signal with the same front end. In addition, transcription dictionary and language model scores are also provided. And as Chalapathy said, we have generated at IBM clean and matched noisy audio lattices. So as a matter of fact, the language model scores are marked on this lattice because the Via Voice data set actually contains punctuation. So we actually need a punctuation language model. As reiterating on Chalapathy's foil, I mean, the lattice only audio only word error rate is 14.44 on clean speech and 48.10 on noisy speech. As far as the visual front end is concerned, there are a number of approaches. I mean, this is the first open research issue on the area of audio-visual speech recognition. There are a number of approaches that have been tried in the literature, and traditionally, like in the older times, people use like parameters coming from the lip contours. So like either like things like height, width, and area from the inner and outer lip contours. You would use things like moments or Fourier descriptors of the lip contours as well, templates or B-splines. So these are like trying to encode information on the outer and outer and inner lip contours of the speaker. These features in general did not perform that well. So, I mean, later on, people started thinking of obtaining the whole region of interest and appropriately projecting that into a lower dimensional feature space. So there are a number of approaches that have been developed for that, and these are like the principal component analysis, obtaining a subsampled whole region of interest as the feature vector, discrete cosine transform, wavelets, and linear discriminant analysis. And furthermore, like even more recently, a number of approaches have emerged where the 2 schemes are merged. Like in addition to grayscale information from the region of interest, also like lip contour driven features are used in addition to that. And there are 2 methods for that. One is the active appearance models method that Iain is going to be talking, and the second method is the active shape models from Juergen Luettin. Overall, I guess the idea behind using video-based pixel-based features is the fact that the region of interest contains a lot of information about visual speech is actually contained on what is happening inside the mouth, and this is information that you cannot actually capture by using just the lip contours. So as we mentioned earlier, like in this workshop, two visual frontends have been considered. The first one is the one I'm going to be talking about, the three-stage cascade image transform using a discrete cosine transform followed by discriminant features like LDA and MLLT. The second model is the model of Iain, which is the active appearance models, and we're trying to compare the two methods as well with a lot of caveats about what is the region of interest, various dimensions of static feature vectors, temporal window size, etc. This is a graph of the visual front end that we're using. So the first stage is actually the region of interest extraction. So at every frame, actually we're using 60 fields per second. We're extracting a feature vector which has a dimension of 4096. So this is a normalized 64 by 64 area. We project this first vector into a lower dimensional feature vector of dimension 24 by using any of the image transforms that we can consider. So like, for example, discrete cosine transform, principal component analysis, or discrete Weber transforms. Now the problem of sort of different frame rates between the audio and the video comes into the picture, and we can consider interpolating the features from either, for example, 30 or 60 hertz to the audio frame rate of 100 hertz. So this gives us like a feature vector at the rate of 100 features per second. And we can also consider applying like a substral mean subtraction to normalize the features per sequence. So this is similar to the approach we use in audio, which we call feature mean normalization and substral mean subtraction. To obtain now, I guess, dynamic information, you can either consider taking the derivatives, first and second derivatives of this feature vector, or you can consider like just concatenating this feature vector and using a linear discriminant analysis projection to find out what are the features of interest. So in this approach, we are using 15 such frames consecutive, 7 on each side, plus the current frame, and we eventually projected using LDA into a 41-dimensional space. The third stage of this processing is just data rotation using a maximum likelihood linear transformation. So the final feature vector is what we obtain here, and it's again of dimension 41. The first problem is the region of interest extraction, and for that we use a statistical phase detection algorithm developed by Andrew Senior at IBM. This is a multi-scale image pyramid search for faces into every frame, which is a statistical method using Fisher discriminant analysis and prior facial part collocation statistics. It requires training, about 2,000 annotated frames on this specific data set, and it has achieved a face detection accuracy of about 99.7% and facial feature accuracy of about 90%. The fact, of course, that the accuracy is not 100% can be countered by using smoothing techniques over a video frame. So to extract the region of interest, we obtain smooth mouth center and size estimates from this algorithm up here. And here is an example of how like these 8 subjects, these are like the corresponding region of interest, which are like 64 by 64 pixels and are pretty much size normalized. Not always this algorithm works that well. For example, here is a Roy failure example where the algorithm erroneously starts tracking an eye and eventually recovers by starting tracking the mouth. So these examples are very rare, but do happen. As we said, after the region of interest extraction, we have 3 transform stages. The first one is a discrete cosine transform, where it achieves, the idea behind the DCT is that it achieves information compression according to the image processing literature. And in addition, is computationally efficient, so this is its advantage over PCA, for example. So the idea is to train over training examples over our database and find the transform coefficients, actually the lattice locations where the transform has the highest energy, and you use this as features. The second stage that we set was the linear discriminant analysis, which assumes a known set of classes. It labels your training data vectors using some segmentation as belonging to these classes of interest, and finally achieves the optimal separation by projecting these feature vectors along the dimensions that achieve this highest separation. The third is the maximum likelihood linear transformation, which maximizes the data likelihood on the original space such that the transform space data class covariances become diagonal. By using these 3 transform stages, the first experiment with that is rescoring the noisy audio lattices, and this achieved like a word error rate of 51.08%. So using these features. This is a completely, we should never consider this as a visual-only decoding result, because this is decoding on audio, noisy audio lattices. I mean, this is just a number to bear in mind, in conjunction with the fact that the random path through this lattice is a 78% error rate. We talked about discriminant features, so here we do a little bit of digression, and we consider how we can use these discriminant features for audio-visual feature fusion. So one idea is, of course, LDA MLLT is actually used also in our audio front end. And similar to the video, like we can use feature vectors of dimension 24, and here we actually use like a temporal window of size 9, and eventually audio feature vector has dimension 60. The corresponding video feature vector, as we said, has dimension 41. And of course, these are time synchronous since we have interpolated between the two. And eventually, we get the audio-visual feature vector by concatenating, and this has a dimension of 101. Now, of course, you can train statistical models on this concatenated audio-visual feature vector. Of course, this has a high dimension, therefore you expect that the data sparseness problem is going to come into the picture. An alternative idea is to project this concatenated feature vector into a lower dimensional feature vector, and we're going to be referring to this approach as an audio-visual feature fusion by this hierarchical LDA method, which we refer to as HILDA. The resulting feature vector has dimension 60, and some preliminary, I guess some results that we have obtained on these lattices. On the clean speeds, we have audio of 14.44%. If we concatenate the feature vector and we train a single stream Gaussian hidden Markov model, we obtain a 16% error rate, so this gets worse. However, by using the hierarchical linear discriminant analysis, the error rate drops to 13.84, so this improves the audio-only result. In the noisy case, the improvement is more like, more distinguished. And from noisy, you get from 48.10. Using the concatenated approach, you get 40%. And using the hierarchical LDA approach, you get 36.99%. So you see an improvement. Yes, Micah?
Yeah, Marcus, could you just once again say what the difference between the hierarchical LDA approach and the ordinary LDA approach?
I would say, you mean why not concatenate the feature vectors here and do an LDA on the whole thing, or would that be the question? Or, practically it's one more. It's an additional LDA MLLT step on an audio-visual feature vector.
It's an LDA step on the concatenated.
On the concatenated feature vector. That's the only thing. Yeah. All right. So one thing that comes here into the picture is the fact that the audio noisy lattices, they have quite a high error rate. So actually, these two numbers, these are rescored by using so-called noisy audio-visual lattices. So what we have done is practically using this LDA model and generating noisy audio-visual lattices. So actually these two numbers, the 40% and the 37% here, are practically like rescoring of the noisy audio-visual lattices. So this 40% would have been quite worse had we rescored actually the noisy lattices a little bit. So this is sort of semi-cheating and making it a little bit better than it should have been. So with this, we continue. Yes.
I guess the question that you raised, why not just concatenate the raw audio and the raw video?
Yeah, that is an interesting issue. We can have it in the discussion later. But overall, you making the LDA work a little bit easier here would have been a really huge vector. Yeah, right, here is a 101. If you do LDA on these things, you're probably having about 700 or something. So,
how does auto-adaptation help in the noisy case? If you just get audio, you have a relative improvement about 25%. That is achievable with just audio adaptation. Do you have a baseline for that?
This is a matched audio conditions, right? We are not.
No, if you do speaker adaptation or anyone adaptation.
Yes, we have done speaker visual adaptation as well, but we don't have done speaker adaptation experiments. But you can say the same thing about doing visual adaptation on top of that. So we don't have a number like that.
We just treated our baseline as matched noise or training. But in principle, we could improve that by adapting to that. I forgot to mention one thing. At the end of our speakers, after the discussion session, we have a featured speaker, Eric Pettigen from Face-to-Face Animation. He's going to talk about MPEG 4 visual speech representation.
Okay, so I want to talk about another completely different, well, related sort of visual feature. And first I should start off by saying what we've done here is actually based on some other work by people like Tim Coots, Gareth Edwards, and Chris Taylor at Manchester, and Stan Sklarov at Boston. So it's not entirely new. Okay, so I don't really have time to go into exact details about how this all works, so I'll just give you like a little overview of the algorithm. So to start with, we can take just any random face image. And the next thing we do then is go through and stick a few dots on. We'd like to do this in real life, but probably wouldn't let us. And this is what we've spent hours and hours and hours and hours doing, is going around and putting these dots on lots and lots of images. And we do this, and we can then just look at all of these and consider them all as XY coordinates, align those all to take out scale, rotation, and translation differences, and do a principal component analysis. So we have a mean shape, some eigenvectors, and some eigenvector weights, which let us basically capture all the variation we see within a few modes. Okay, so the next thing we can also do is do a Delaunay triangulation on these, which is just fill up the space with triangles. We can then cut out, obviously, just the area that we're interested in. This is exactly the same, just without the mesh. And then we can warp that to a standard face shape. So you can see Fred now has a slightly open mouth. The way we do that is just per triangle, affine warp to here. So it's exactly a texture mapping operation, so it's not very hard. Again, because this is always exactly this shape, we can sample the pixels out of here, do another principal component analysis, and we have something a lot like an eigenface, but that's shape normalized. Okay, and then as a final step, we do another PCA by taking just the principal component values from each of these with a weight, because these are XY coordinates and these are pixel values, so we need to, they're different units. Another PCA gives you a final concatenated model, and that's what we'll be using. Okay, so how does this relate to what you just saw from Makis? He has to use the face detector, and we have, I won't really talk very much about it, but you can actually use this model to fit itself to the data, so there's a tracker. Okay, and the other thing is then he has a predefined box which he has to basically deal with. He just samples out of here, and we can explicitly model whatever shape we want. We don't have to worry about anything happening in the background. He then does a DCT or any other transform on this box. We can now read directly the features we use to find this from this model. And we're also free to model just lips if we want, or we can just model, say, a beard region if we expect those to be the only parts that move while you're speaking. Okay, so this is actually 1/4 of all of the training data for real, played one frame after another. So this is what these people look like at IBM. We actually have 4,000 training images, which is actually only 2 minutes and 13 seconds out of 50 hours worth of data. So we've labeled a really, really tiny amount of data, and this took a hell of a lot of work. And so you can see there's a few errors in here, and basically we're getting a few frames per person. We basically know what their face looks like. We don't really have a great deal of information about how they talk. Not very many young people there. Okay, so then we build this model. There's a mean shape and appearance, and we can sort of project this plus or minus 3 standard deviations along. This is the top 6 eigenvectors. And you get something that looks like this. This is exactly the same, just plotting it out just to show you these are real linear combinations. And because it's a linear model, we can separate appearance and shape even though we've combined them. So this is what the current appearance is, the current shape. You project these two together, and you get something that looks like that. It's also pretty obvious in here that a lot of these are sort of speaker dependent. These two people, this person, they're all in the database so that you can sort of still pull them out, which is a little bit nasty, really. Okay, so how do we then fit this to an image? Again, we take an image. We just initialize at the mean shape and mean appearance, throw that up in the middle of the image. So we can now sample what's underneath that image and warp that to the same reference frame as this. So for now, we're just using the mean shape. So we take what's actually in the image and warp that back to the mean shape. It can take the difference between those two, and this, we hope, if you're not too far away, tells you some information about what you need to do to fit this model to the image. And it seems to hold as long as these are just small perturbations away. And actually, when we train this model, we generate loads and loads of these, build a linear regression model, and we can use that to give us a predicted update, and we can weight that. So we have a predicted update, gives us some new model parameters. This may be wrong, so we can play with the weight on that. This gives a new appearance, a new current model, a new image under the model, because this may have moved, a new warped image under the model, and a new difference. Okay, so we can then measure that error, see how it changed from the last time, change this alpha weight, and go all the way around again until either we start increasing the error or we run out of iterations. Then we can start again with a new predicted update and carry on going around again until this converges, which is usually not more than 3 or 4 iterations on an image. And this C here is actually not just the principal component values, it's the translation, the rotation, the scale. That's an appearance transform, so we can make this brighter and scale it. Plus, I don't know what that K is. Plus, that should be dots, I think. Plus the model value. So it's everything all in one go. We just go, where do you want to go? And it moves itself and updates its parameters. Okay, so what do we get when we try tracking this? And there are 2 movies here. This is the worst one, and this is the best one on the data we've actually run it on. This number here is the mean square error over the sequence. So it's, for any frame, we can calculate the error between the model and the image underneath, and just average that over the whole sequence. So you can see it's roughly on his face, but a lot of the time it doesn't really know what to do, and it's not tracking him speaking. And this one is a little bit dark, but it's actually most of the time following his lips, and is a pretty good fit.
When you say it's not tracking him, are you basically saying that you're warping him to something so that the lip motions are just indistinguishable from random noise?
No, I mean, this model is trying to fit to the image. Think of it as the image being underneath it, and you're laying this on top. So I'm measuring the error between this and what's underneath. And this clearly didn't track him. This is the original image. This is just it laid over the top. And if it can't find a lower error point at any given iteration, it just stays still, which is why this thing stays still, jumps a bit. And so this is basically, the tracker has failed to do anything. I like playing that movie a lot. Okay, so we actually ran this, we managed to run this on 5,000 sequences, so it's not the entire database, but it is over 1 million images, which is about 10 hours. And if we find our mean square error over the entire tracking set, it's about 254, and we managed to track down at about 4 frames a second if we ignore the MPEG-2 decode time. And we also did try these beard area and lip area models that I showed on an earlier slide, and they won't track. There's not really enough texture in those regions to get a good, accurate track. Okay, so this is the sort of features you get if you plot these over time. This is what the model generates, so we can just synthesize it back out. There's a disembodied face, and there are some features just tracking them just to see what they look like. So what does that give us? We're rescoring the audio lattices. These experiments are actually, you can't really compare these to what Marcus showed because his was over the whole database, and given the time we had here, we couldn't actually manage to do all of that. So first thing we can do is just dump all of these 86 features, use those, and we get an error rate of like 66%. Or we can take just the top 30 of those because these are PCAs, so they're ranked in order of variance. So we expect the top 30 to have, the top 30 is about 85% of the variance, and 86 is 95. And we don't lose very much at all. we can add deltas and deltas to this 30, and it actually gets slightly worse. But these are interpolated features, so this is probably to be expected. A lot of the time they're going to be 0. We can do something very similar to what Makis did with his features, which is, apart from the fact that we use an LDA on the 86 features, take that down to 24, and then do exactly what he did with an LDA with a window, and we get slightly better results. But Makis, with his DCT features, can do better. If we just take raw DCT with deltas and deltas, 62, and if we do the LDA, 58.14. And then the really interesting thing here is that if I just dump 30 vector of noise, we can get 61.4. So we're actually, by dumping random noise as features, building models and rescoring the audio lattices, it can actually beat most of these. So this is a little bit strange. So if we actually plot these per speaker, you can see the differences between speakers are very similar. And these are completely different features, and these ones are even just noise. So something's actually happening here. And basically, the language model and the lattices we've used are basically dominating this experiment. So I can't really give you numbers that said, here we did this much better than DCT or anything. I can just give you the numbers at the moment that we got. So that's really just an artifact of the way we did this experiment. I can also plot things like what the tracker errors were like compared to the recognition results, and these are clearly not correlated either, and we'd expect those to be. So in summary then, our models are really, really undertrained. We managed to get a whole 2 minutes worth of training data, which is clearly not enough. And we're not really doing very much more than face detection. Things we can do to improve this, obviously we're not really interested in the eyes and the nose because we want to do speech reading, but we can't track this model. But we can easily track using this model, take the results, reproject it through this model, and just use parameters like that. We can easily try that. And another thing we can do is this reference shape is just the mean shape. It really needn't be. If we're more interested in what's going on in the mouth, we can distort this and turn Fred into some sort of frog. And maybe this is the best sort of reference shape we can have. Basically, we want to minimize the information loss we get from this warping. That's it.
I'm going to talk about one of the problems is the visual feature extraction, and another big problem in audiovisual speech recognition is the combination of the audio and visual information. And here the problem we try to solve is we would like to get the best word string given both acoustic and visual information. And using Bayes' rule, we can transform this into probability of a certain word string given the acoustic observation and given the visual observation. Now, the question is at which level do we combine both of those information, acoustic and visual? Another question is, together with this question, we would like to find out if the acoustic and visual information are conditionally dependent. So two extreme approaches can be classified or named as early integration, where we just combine the features at the feature level. Another extreme approach is where we perform independent recognition of a visual speech recognition system and of an acoustic speech recognition system, and then we combine the hypothesis somehow, for example, by combining n-best lists or so. So the integration at the feature level basically assumes that we concatenate the features. Then we train speech recognition systems on those concatenated features. And this assumes that the two streams are conditionally dependent, and it's integration at the feature level. this is the other extreme approach where we have two separate likelihood estimations on the for a visual model and an acoustic model. And Dimitra is going to present a technique using this method. Now, one approach between those two is we model both of those information streams in one HMM, but we are having two different streams on each HMM state. So the difference this makes is we basically, here in the probability density estimation, we have two components. One is the mixture, Gaussian mixture of the acoustic stream, and the second one is one of the visual stream. In addition to this, we can weigh both streams. This might be important, for example, if we have acoustic noise. And this approach is based that those two distributions are conditionally independent, and the integration here is on the state level. Now, a different approach is there's some evidence, or there's some suggestions that the acoustic and the visual signals are not in synchrony. For example, mouth movements, they can precede the actual acoustic signal. I can move my mouth without making any sound. But on the other hand, for certain phonemes, for example for P, for plosives and so on, the mouth movement has to be in synchrony. So with if you have such a model, we can account for asynchrony that can appear between both signals, but we can also, at such points, we can enforce the signal to be in synchrony. So this makes the assumption of conditional independence between the streams, and the integration of those two is at the unit level. Like in our case, the unit is based on phonemes, and in the decoding here, we basically have to find the best path for each of those two streams. So we find the best path for the visual model and the best path for the audio model. Now, a different realization of this multi-stream model, because we have to optimize those both streams at the same time, is we can transform this model into a composite model. This has first been proposed by Varga and Moore for speech-noise decomposition, and by Dupont and Luettin for audiovisual speech recognition. So we can transform that multi-stream model into such a model where we have here on this axis the acoustic states of the HMM, and on this axis the visual states of the HMM. So our decoding is not based on finding two separate optimal streams, but finding the joint best stream of XAV, where XAV is a combination of both states, the acoustic and the visual states. And the observations of each stream, they are the same as we have seen before in the synchronous multi-stream model. The transitions, they are decomposed into more components in this model. So instead of, for example, here, staying in state, in the acoustic state 1-1, this is composed into three components now. So, which is one of this, then this transition, and this transition. Oh, I'm sorry. This one, and this one. And similar things can be made for other transitions. And in addition to this formalization, we can also model we can limit the amount of asynchrony we allow to our model by limiting this difference between the acoustic and the visual state by a certain integer, which has to be smaller than the number of states. To implement this composite model, we would like to we would like to avoid an increase in parameter estimation. So if you have this would be a synchronous model where we have in synchrony the acoustic and the visual states, and those are the asynchronous states, and we can actually tie part of this state, like just a visual stream, to this state, and for this state we can tie the acoustic stream of this state to the acoustic stream of this one. So we actually, all those off asynchronous state, we don't have to estimate any new parameters. We can tie them to the synchronous states. Well, here's a description of the audiovisual speech recognition system we have developed. It's based on 3-state HMMs with 12 mixtures. In the case of the composite model, we have used 7 states. Context-dependent phone models using 2 silence models. We have done clustering, state-based clustering using decision trees. Using crossword-dependent context-dependent decoding on lattices computed at IBM. It also used a trigram language model. And the stream weights between the acoustic and visual, they have been optimized for all those experiments on a held-out test set. So this was the same system that has been used for all experiments shown on the next slide. There hasn't been any change. For example, we have used the same tree-based clustering, the same number of mixtures, and everything was the same. The only thing that has been optimized was the weight for the language model and word insertion penalty. But there was only a rough optimization. Here we have again the error rate for the clean system, using acoustic features only. Here, those are the results using the audio-visual features based on the hierarchical LDA presented by Makis. This is the result for the early integration where we just concatenate the 2 streams, so we actually see the recognition rate gets worse. This is the synchronous multi-stream model, and this is the asynchronous multi-stream model. Those are the results for the noisy conditions based on the lattice that has been computed using the acoustic model. The acoustic model that has been trained in matched conditions. So we see the audio system has an error rate of roughly 48%, and the video has an error rate of over 50%. And all those combinations, they reduce the error rate by about 5% or so. This column shows the word error rates for using lattices that have been computed on an audiovisual model. So those lattices are already much better than the ones using the acoustic-only model. And it can be seen that the first, the concatenated features, they make the results worse compared to the hierarchical combination. The multi-stream model, the synchronous, has about the same as the hierarchical LDA, and the 2 streams with the asynchronous streams gives us the best results.
Excuse me, I saw that Chalapathy said you are going to do the have a number for the random path.
I had it in my slide.
But wouldn't we want it here?
Well, yeah, it's
So what is it?
it's the 78% on this noisy lattices, and it's on the clean lattices it's 44%.
I see. And when he says video, when you say video, that's just that just finds the that's not the correct path, but it's trying to resolve the uncertainty of the lattice.
So
And
you take the lattice and use the visual models only
Yes.
to report the lattice.
Yes. So video itself gets from what, 17% down to 52.
Right.
Also numbers model.
With
So
the
this
numbers
is this is video model rescoring on the acoustic lattices, on the matched
But the
lattices.
The language model gets it to 60%.
I
So
see.
with the language model, you get
So the language model also improves by about 5% or so. I've made different.
But in that case, you ought to have a measurement of what is the best lattice path resolved only by the language model, right?
Yeah, this is actually in light of the noise results that are presented by Iain Matthews.
Yes.
It looks like that's around 60% or so. But
The
we don't
language
know.
model itself is 60%.
We don't
So
know
the
yet.
reduction is from 60 to 52 or something.
But this is sort of a guess. We have to do that.
It's hard to estimate what only the visual models would give us because we are always using the lattices that have been obtained from the acoustic models. So we always have information from two components.
I mean, visual could do anything for you, right?
I'm a little confused. I thought the noisy lattices are lattices we generated at IBM in advance off of noise-corrupted speech data, correct?
Right.
Now, what are the AV lattices?
You actually do take audio-visual Hilda features and then generate lattices based on that.
Okay, we also supply those
Yes.
as well. Got it.
Because those lattices are much
All
better.
lattices were supplied
Well,
by
I was, okay.
So this improvement is just due to the better lattices on the audiovisual models.
So I actually I'm calling the noisy AV lattices hierarchical fusion because you're actually generating the hypothesis itself using the audio-visual combination and using a different model to rescore.
So some conclusions on those experiments. The asynchronous model gave us slightly better results than the other models. However, the asynchronous model has just been a first implementation and nothing has been optimized. For example, one big advantage of this model is that we can model different asynchronies, and we really should look at the transition matrix. For example, here we have used the same transition matrix for all center phonemes. So we haven't used any context-dependent transition matrices. And I think there's a lot of improvement to be gained by using context-dependent transition matrices, where we can look which transitions have been preferred by certain context-dependent phonemes. We can also, what is this asynchronous model has many transitions, many transition probabilities. And even if we have a transition probability which is very small, if we do the decoding, this transition probability won't have much effect in the decoding. So one method might be to just prune transition probabilities that have a very low transition. Another thing is the stream weights have been global here in this approach. So they have just been optimized on a held-out set. And Herve is going to talk about the different system where the stream weights are estimated per sentence basis. And other methods are also what Dimitra is talking about, where the models are, the weights are based not only on, we do not only use global weights, but we have phoneme-specific weights. And another open question is the clustering. We have used the same clustering for audio and for visual and not for audio visual, so there might be further improvement to be made.
Okay. Okay, so I will talk about a method of fusing the two models, the acoustic and the visual model, weighting separately the scores of each model for individual units of the hypothesis. This is the formulation of this approach, called discriminant combination of audio and visual models, which is actually a late and synchronous kind of model fusion. We defined the product model for combining the audio and the visual scores, just like Juergen explained before, except that here we see that we have a different weight for the acoustic score and a different weight for the visual score for the hypothesis, which still keep the language model weight. In this model, we're going to train the weights to minimize the word error rate as induced by the whole product model on the hypothesis. A further modification of this is to have weights that are actually dependent on the hypothesized units. These weights could actually be trained to use more information than just what the unit is. Like in this experiment, I only used the phone identity as the parameter for the weight. Actually, I used only the phone identity to train the weight on, but you could use other information like relative confidence between the visual and the audio, or signal-to-noise ratio that Herve was doing. Anyway, so the weights in this experiment can be tied within a class of phone models, and there will show results where for the visual model, the weights are defined for VZIM classes. So we have 13 VZIM classes, and the weights for the audio model are actually defined for each individual phone. This is a summary of the procedure. First, we need to do N-best rescoring with this method. So we obtain N-best hypothesis using the baseline system, which includes the best acoustic model we have and the language model. Then we rescore the hypothesis with the visual models. And this is a way we obtain a model alignment. So we have, for each model, what is the score for each segment of the signal. Then we combine the scores for each hypothesis in the product model, as I showed in the previous formula, and we optimize the combination weights to minimize word error rate on a held-out set. This optimization is done using the downhill simplex optimization method. Finally, we rescore the N-best hypothesis using the product model. Okay, so I only was able to run the experiment on the clean audio lattices. Okay, one thing I should say here is that the baseline I have is 13.65, which is better than the baseline presented earlier with the acoustic models. And this is an artifact of rescoring the N-best hypothesis. So I had N-best hypothesis obtained using the IBM acoustic models, and then I rescored them using the HTK acoustic model that Juergen built. And this way obtained a baseline of 13.65% on the test set. In the case where the visual and acoustic weights were optimized globally, meaning we had one acoustic weight and one visual weight, we see a small improvement. And when we include 13 VZIMic weights for the visual model, the result doesn't change too much. The final line, we see the result using how many? 56 parameters. We have 43 phonemic weights and 13 VZIMic weights, and that goes to 12.95, which is, that's it. Okay. Excuse me? There are about 1,000 hypotheses. How many was that? 1,000 utterances. MS check.
Over 2K. Yeah. Over 2K.
4 hours.
If you had only used 43 phone classes in the audio system, forget the video.
No, it doesn't help.
I just want to make sure.
She tried it.
So the results we've shown already are for global stream weights according to some optimization and the held-out test set. And the weight we used were 0.7 for the audio stream and 0.3 for the video stream. My work was mainly to find an automatic way to find these weights. So first, we were working with a multi-stream model, and we had two strategies to build this multi-stream. We could have a global training of two synchronous streams, as Juergen shown before, or we could make two independent training with the same clusters but different elements, of the audio model and the video model, and then create the multi-stream audiovisual model by coupling in each state the two streams. We did two experiments, and the best model was with the global training. So we used only the global training after. And then the weighting factors will be alpha for the audio stream, and 1 minus alpha applied to the observation of the visual stream. So alpha should depend on the confidence of each stream and on the signal reliability. Ideally, we should need a reliability for each frame, but in our approach in this workshop, we use the global weight on all the sentence. First, I tried to see if we could have different weight for silent state and all the other states. So I tried first in clean conditions to weight differently all the speech states here and the alpha for the speech state. So here you have alpha from 0 to 1 for speech, and from 0 to 1 for silent states. And you have the word error rate. Black is for 13 word error rate, white is for 30% word error rate. What we see is that for the clean condition here, speech and silent sets shouldn't differ, really, and the best values are around 0.7. These are experiments done on the held out test set, only 16 sentences because it needs a lot of experimentations to have many dots. So this is in clean conditions. In noisy conditions, the conclusion is rather different because we see that the silent states should be higher than the silent state weight for audio should be higher than the audio speech states. I mean that the variation of the alpha for speech should be bigger than the variation of the silent state. So the conclusion is that ideally we should have a alpha function for the silent states and the alpha for the speech, and alpha of silence should be higher than the alpha of speech. But anyway, the next experiment I did was just about one global weight applied to silence and speech states. So we will have to find a global weight, and we can take advantage of the relative contribution of acoustic and visual modalities. Speech features have one more modality than visual features. They have the voicing modality. And so our idea was to use the ratio between the voice-speech energy under the global energy of the signal as alpha. So we computed here a measure like an SNR measure. So signal energy by signal plus noise energy, so this ratio, versus the HNR. So it's only harmonic energy by the speech plus noise energy here. And we see that on the whole test set, they are well correlated, but on the bubble speech noise at 10 dB. So here is a sample, 1 neuterons on the noisy speech. And what is interesting is that HNR gives more information about harmonicity, about voicing, of course. Locally, we can see, so here it's a time by frame, and we have the dots for each 128 millisecond frame length. In black, you have the reference, a priori SNR. In pink, it's HNR, which is estimated. And in blue, it's HNR on clean speech. So we see that in very high voiced place like here, HNR is higher than SNR. And in contrary, in low voiced place like here, SNR is higher than HNR. So locally, we have an information of voicing, and we need now to extract from this HNR a global weight for all the sentence. So what I did is that I considered only the values which were higher than threshold, which is 0.5. 0.5 is a value for SNR corresponding to 0 dB. So for each of the frames which have more than 0.5 HNR value, I take the mean of all these values, and it gives me the alpha weight. This alpha weight, which is the mean of all HNR higher than 0.5, as we see here, for all 500 utterances, it differs on each utterance and in each speaker. In this plot, for clean and noisy conditions, noisy is in red, we have the set of the first utterance set for the first speaker here, second speaker with all the sentence from this first speaker, third speakers, and we see that in the first speaker, the voicing is less than the second. So we will use in the experiment in clean and noisy the value of HNR, the alpha value, contrary to the previous experiments where we were only using 0.7 like the audio weight. And remarkably, we see that the mean of alpha across all the utterances is 0.79, which is close to the optimal weight we found. And in noisy, it's 0.73. So the results of lattice rescorings. Here we have the baseline with independent training for clean conditions. Here is the baseline for clean conditions of the global training multistream. And here with a global weight 0.703. And here is the results using alpha, an alpha different for each sentences. Okay, so the baseline is 14. No, it's 1462. The baseline is 1462, and it gives somehow 10% of improvement with local weight. And here it's the same with noisy conditions. So the baseline here is 3660 something, and I've got also 10% improvement. But it's very long to compute for each sentence different weight, and here it's for 1,000 sentence, and here for 80% of this 1,000 sentence. So, but it shouldn't differ with the whole set. So globally, we have 10% improvement in noisy and clean. The next step is to use a nonlinear function of HNR or of the alpha used, to use an alpha, a different alpha for silent state and speech states, to use, like Dimitra suggested, different alpha for different phoneme classes according if they are voiced or unvoiced. And the ultimate experiment will be to use alpha at the frame level. This should be much more interesting because, as you you have seen in the plot the variation of alpha is interesting locally in the frame level. That's it.
Actually, June's going to talk about what you can measure in the visual data, so that's probably true.
Okay, so I'm going to talk in particular about the use of the visual data in clustering the triphones. So this is part of the training, and prior to this, the monophones and the triphones have already been trained. So this is the clustering of the triphones. So in talking about this, I'll start off to define the visemes, and actually these are flipped, I'm just realizing, and the goals of using the visemes, which are the visual data that's the sort of terminology we coined for the visual data, or the visual behavior of the phones. And then talk a little bit about what we found in inspecting the phone trees. In doing the clustering, the issue of equivalence classification is brought forward. And in fact, the equivalence classification is applied to try to assist with the problem of data sparseness. But also it's important that when the classification is applied, that the classes come up frequently enough so that it's not just a crude measure of frequency counts, and that it actually can serve to predict. For our purposes, we use decision trees to achieve these classifications. In particular, we were clustering triphones, and in talking about triphones, as you know, we dealt with the issue of the co-articulation, so the context context dependence issues we dealt with within the triphones. So in general, to derive these classifications, you collect a lot of speech data and classify these into appropriately distinct categories. So here's sort of a tree which tells you a little bit about what happens in using the decision trees. So here in this example, this is the third state. The states are numbered, and I'll talk in those numbers because I'm used to it, as 2, 3, and 4. So in this case, we're talking about the third state of the phone AW here. And so what happens is, and in particular, actually, I'll be talking about the root nodes of these phone trees. So at the root, the first question gets asked, and that question partitions the phones into two new sets. And once when the partition occurs, then there's a sort of mechanism for trying to define, trying to maximize information gain, but also to try to balance the number of, balance the partitions so that the same number of items are on both sides, so sort of a balanced tree effect there. And so that occurs, and when the question that is asked here maximizes those two criteria, then that question is kept at the root, and we move down, and the same process occurs at this node, and then at this node, and further moves down until you get to the leaves. So this is sort of backwards, but the definitions of visemes, again, it's sort of the terminology we coined for the visual data. In the literature, if you look, they talk about canonical mouth shapes and often show little pictures. And it's meant to complement the phonetic stream. That is to say that when you have acoustically confusable phones or phonemes, the hope is that the visual information will give you some assistance in giving you information. So for example, me and ni, which are acoustically confusable, are visually distinct. So me starts off with the lips closing, and ni does not. Another classical example is f and s. So while those are acoustically confusable, visually they're distinct. So in doing in creating the questions that allowed us to do the questions that occur at each node of the decision trees, we took acoustic questions, which, if you look here, manner of articulation, the rows here are how the questions that are acoustically driven are broken up. And so you see nasal stop, fricative, etc. For the visually based questions, or the Vizim questions, we looked along the columns, the place of articulation. So for instance, one Vizim class became the bilabials, the pa, ba, ma. And another Vizim class was the labial dentals, the f and the v. So this worked very nicely for the consonants. For the vowels, we used the parameters of, or we used the issue of decreasing lip rounding. And so these have the least amount of lip rounding on down. And you can see this third and this last Vizim class this is a combination of the two above it, and this is a combination of the two above it. And those were empirically based. So from reading the literature, we found that actually those were Vizim classes that were used, so we decided to try it. All right, so you have to split this chart sort of in half here. This is the actual corpus of questions, okay? And these are results. So first, the corpus of questions here, there were 276 questions in total. 76 of them were visually based, and as you saw on the previous slide, the Vizim classes were, for the consonants were along the place of articulation, and the vowels were as such with the lip rounding. Audio was 116. And then there's another class that we called single phoneme. And the best way to describe that, and I'm looking right at Gina, is when you think of these questions, these questions have a certain amount of specificity. These questions are sort of looking at visual behavior of the phones, and they're more general. And these are sort of more general about audio behavior. These are wait, let me back up. These are, again, we use in this case the visual data as a context. Okay, here we go, forward. And so in the case of here, the visual classes are used as a context for the phones. Here, audio context is used, and these both are more general. These are single phonemes, and these are very specific. Okay. Did that make sense? All right. Okay, this is one, one visual class. This is one Vizim. This is the pa, the ba, and the ma. Okay, across here, this is the p, this is the b, and this is the m. This is the second state. These are the phones are broken into 3 states. And so here's the second state of the P, the third state, and the fourth. The second state of the B, the third state of the B, and the fourth, and so forth. Don't pay so much attention to what is inside the box. Pay more attention to the number of things in the boxes, okay? And so in doing the inspection of the tree, what we tried to do is we tried to look by phone within a Vizim class. So we looked at what was occurring within the P here, and what was occurring within the B here, and what was occurring in the M here. And you can see that generally speaking, what we decided was that specificity, how specific the question was, sort of could be understood by the number of stuff in the question. So this was not a very specific question, and in fact, there wasn't much information to be gained here. This, red flag, is a very specific question. Now remember, these are being asked at the root of the decision trees for each phone. This again is a very general question, not much information. This is a more specific question, and this is good information. You can see with the M, for 2 of the states, we got very specific questions at the root. So at the root of the M in the second state was this question, and these were red flags, because you think about it, when you're parsing a tree, when you're partitioning a tree, to have such a specific question occur at the root is kind of odd. You can't imagine that the M at the second stage is always going to have this to the left of it. Yes?
I'm not sure, which data are you classifying? Are you classifying the video data, or are you classifying the audio data?
Yeah, we're talking about the phones. Okay, so
We're classifying the visual.
Visual data.
We were trying to develop visual models that are more specific, so wanted to find out whether there were visual questions that are more important.
Right.
And so, in conclusion, actually, I just realized that the one slide is gone. So where we expected some similar linguistic contextual behavior between phones, instead the data seemed a little bit unbalanced in that some of what was occurring seemed to be an artifact of the data. So.
So I'll be talking about the visual models that we created. I'll start by telling you about the 3 models that we had, some of our results, which are generally flat, and some analysis and some future outlooks. So we had 2 sets of questions. The original set was 202 questions based primarily on voicing and manner of articulation. And June created a second set. I think that number is slightly wrong, but it's about 274, or I think 276 questions, and which includes the original 202. And this primarily includes questions based on, this includes in addition questions based on place of articulation. And using these, we made 3 models. So the initial model, the audio clustered model, we used the original set of questions to develop decision trees based on the audio data. And we then forced the visual models to cluster from the same trees. In the second model, the next 2 models are self-clustered. So in both cases, the visual data is clustering itself. In one case, using the old questions, and then using the new set of questions. And we want to look at 3 major factors. To what extent are the 2 data streams complementary? So if the visual and audio streams are more or less redundant, then clustering based on the audio would do as well as clustering based on the video alone, video itself. Also, the quality of representation and the success of our generalization mechanisms are sort of evaluated as a whole. You can't really take these things apart very easily. We used a speaker-independent set, and again, it was just rescorings of the noisy audio lattices, which ended up creating some problems. And these are the results. So the purple ones are with the original questions, and the green ones with the new questions. This is clustering based on the audio models, and this one's self-clustering. So clustering based on the audio did slightly worse than the other 2, but it's not significant. And in fact, the best clustering was with the original questions. So it doesn't seem to be a big difference. There's no major benefit coming from the new questions.
What's the difference in the number of classes that you see?
I'll talk about that in a second, the number of clusters that. So we then look at the per speaker results to see if maybe some speakers are getting better with visual clustering with the new set of questions. And this is actually not a time series, it's per speaker. These results followed the same pattern, had the same variation across speakers as the noisy audio. And that was because we were scoring from the noisy audio lattices. So to remove that, we subtracted the noisy audio word error rate. That's why these numbers are low. They're generally 12%, quite a bit higher than the noisy audio evaluation. And in some cases, the visual questions give you an improvement. And in about as many cases, they make things worse. So there's no overall difference, even per speaker. And again, so the speaker variability of the visual models follows that of the audio because of the lattices. But this does not necessarily mean that the fact that the visual accuracy and the audio accuracy are correlated doesn't mean that the two sources are not complementary. Because while the average for a given speaker may be more or less the same, for particular phones, it may be that the visual is much more informative than the audio, and vice versa. And we haven't been able to look at phone level performance yet. Also, Viseme clustering gives better results for some speakers only, but there's no overall gain. It's not quite clear why that is. This is a disappointment. And so we wonder, are the new questions being used? Maybe only some of them are being used, and they're just having it generally. They're not very helpful. But we in fact looked at the ordering, and they are being used quite frequently in the new trees. And they're also changing the ordering of the old questions. So some of the old original questions, which weren't very useful, now are used much more frequently. So one potential problem is that the new models are overtraining, or possibly both models are overtraining. We have about 7,000 clusters in the models, which is about the same number that appear in the audio. But the audio has 40 phonemes, whereas the visual has only roughly 12 visemes or visual clusters. And if you expect that the number of clusters should be roughly proportional to the cube of the number of phonemes you have because you're dealing with triphones, you would expect something like 200 clusters for the visemes. So we actually did an experiment with fewer clusters. The other possibility is that because the clustering algorithm is greedy, it's trying to optimize locally. So the overall clustering you're getting with the new questions could be suboptimal. So there are several ways to reduce the number of clusters. You can increase the minimum cluster size or increase the likelihood gain threshold. So when the algorithm decides to break up a cluster, it picks a question and looks at how much improvement it gets in the likelihood. And if it's above a certain threshold, it breaks up the cluster, otherwise it keeps it. So if you increase that likelihood gain threshold, you'll increase the number of clusters. We can also remove some questions, especially those that are used at higher depths. So more specific questions that may be tuning into patterns that are specific to the training data, and not necessarily general, or any combination of the above. So in one experiment, the only one that we've done so far, we tripled the likelihood gain threshold from about, I think it's 300 to 900. And that cut the clusters down to 500, but it didn't really help us. But again, the number of clusters we might be good to test is around 200. And we haven't had a chance to test that yet. So as it is, it got a little worse. But we may be just far off in the suboptimal region. Also, other reduction strategies are worth considering, such as removing the questions or removing some of the audio-based questions and using only the visual questions. So a few things that we're planning on trying is, for one thing, getting better clustering parameters in general for audio clustering, because the values we're currently using are optimized for MFCC audio models, and which are quite likely not very optimal for these visual models and Fisher sets. Also clustering using only the Viseme-based questions, again to reduce the number of clusters, and looking at errors in recognition of particular phones, and seeing if particular performance on particular phones improves with the visual clustering as opposed to the audio clustering. And I'll pass it over to Jie. He's going to talk about some annotation experiments. Are there any questions?
Since each of us has our unique set of characteristics, speech characteristics such as accents, the speaker-independent system cannot adequately adapt, or shall I say, cannot adequately model everybody that comes along as a new speaker. So that's our problem with the system. And the solution is to use the adaptation so that we can make the speaker-independent system to better fit the characteristics of each new speaker. And in this case, only a small amount of data is needed from one new speaker, and to use this speaker-independent system so that we can fit the characteristics. So let's look at adaptation mathematically. The new estimate of the adapted mean, mu, is obtained by using the transformation matrix, and the formula is given by mu equals W epsilon, where W is the n by n transformation matrix, n is the dimensionality of the data, and epsilon is the original mean vector. To see this graphically, we have the Gaussian distribution of the speaker-independent data, where the solid line indicates that there's a lot more data for the speaker-independent data than the speaker-specific data, which is, in this case, the dotted line. And what adaptation do is that it shifts the mean, the original mean vector, to the new estimate of the mean mu. And I thought this would be understand more. The process starts with the HMM model with the mean vector and the variance. It feeds into the HE adapt along with the speaker-independent data. And what we get out of it is the transformed speaker-independent model, where the new estimate of the mean is obtained from multiplying the original mean vector with the transformation matrix. The last step is to test whether the whole adaptation process was successful. And here we need to use speaker-adapted test data and to perform recognition. So we did a speaker adaptation on visual models using MLR, which is maximum likelihood linear regression. Also the single mixture triphones and global transformation, which is just one single regression class tree with one root node. And the amount of data we have is about 5 minutes average for each speaker for adaptation data, and 6 minutes average for each speaker for test data. And it's overall for 10 speakers. The result is listed in the following table. And we see that there's a consistent improvement for all speakers, where notice that there are several significant improvements for some speakers over here. And the average turns out to be around 3% overall improvement for the word error percentage. This result can be further improved if we use multiple transforms instead of single transforms. Mixture Gaussians in the model can improve both systems. And finally, we can also try to use other methods of adaptation, such as map. And hopefully, with more data, we can improve this process a lot better. And thank you for your attention.
So that basically ends the presentation section. What we'll do based on Fred's suggestion is take a break, come back, I'll give you the conclusions, and we'll have the featured speaker, Eric Pettigin.
Yeah, let's come back in 15 minutes, which means at 4.
Okay, let's resume the session. The way I would like to do this part of the discussion is I'll summarize our results and give you some conclusions. We'll have the questions, and at 4:30 I'd like to have Eric Pettigen do his talk before the session ends. So let me say a couple of things here. My expectations for the workshop actually have been surpassed in terms of the number of experiments we actually did and got the results for. Every experiment that I wanted to get a result for, the team actually did get results for, and more. This is just an indication of all the things that we wanted to do and did get done. So this is roughly a summary. There were, again, as I said before, there were really 3 types of fusion experiments done, where we assumed a dependence between the 2 streams, which we call feature fusion. Then we had state level synchrony, which we call the AB1 stream here. And then we had the so-called Hilda feature fusion, where we had a 2-level scheme where we actually had discriminant features coming from audio and video that's concatenated together, followed by another LDA on top of that, which is also, again, feature level fusion, but using discriminant features. Multi-stream MS is the state level synchrony, and PD here is the product model, or allowing asynchrony within a unit. Here we considered it to be a phone. And the so-called HIF here are the hierarchical fusion, where we actually generated the lattices using a joint audio-visual model based on the Hilda features and rescored them using various fusion strategies. Again, multi-stream, asynchronous model, and the PDAF is Dimitra's phone-dependent utterance level weighting schemes. So to essentially say 2 things here. One, starting from a baseline of about 14.5, we actually were able to improve on the clean data, which I think we haven't done so far. In this workshop, we have shown we can get some small improvements in the clean as well by doing audiovisual fusion. And the other thing is on the noisy features compared to the matched noisy audio result, which is, apart from some adaptation and additional compensation schemes, gets close to what we can do for that condition. We were able to improve about 27% relative by doing this 2-pass fusion scheme. So this is essentially what I just said. Small gains on clean audio. Both hierarchical LDA and phone-dependent weighting schemes achieved that. Significant gains, in my point of view, for noisy audio using 2-pass schemes. Visual modeling, as you saw from Iain's results, the fact that over noisy features, we are not really able to improve either using DCT or AM suggests that there are certain limitations to the schemes that we have. In other words, that in the absence of strong evidence at the acoustic or the visual feature level, the language model is going to dominate the result. And I think this suggests that we really need to improve upon the amount of information that we can capture and should capture from the visual stream. And I just said that. So what are the open issues? You saw one scheme where we went from the region of interest estimation, that is the mouth region, to Iain's scheme where you actually looked at the entire face. And he suggested in his talk that maybe rather than look at the entire face, you would look at the beard region. It's been suggested based on a group in Japan that you could actually not just look at the mouth region, but look at the cheeks and the jaw. And he did a synthesis just based on the visual information. And the audio on the synthesis was reasonably intelligible, which suggests that there's a lot more information in the cheek and the jaw movements over and top of the mouth region. In addition, for certain languages like French, for instance, lip protrusion is a very important element of the visual aspect. And going to 3D models may be more appropriate. clearly, we have seen that tracking needs to improve. We have a lot of noise in the visual region as well, because we get gnosis as lips in certain cases. The other notion that comes up from Ken Grant, who has done a lot of work in deaf subjects, suggests that, an obvious statement which says that the only thing that is available in the visual stream is the place of articulation. That is, things like bilabial closure, labiodental closure, and so on and so forth. The question is, it looks like 2 or 3 bits of information are really sufficient to encapture all that is given by visual information. Does it make sense, rather than a transform representation, to actually boil it down to just these pieces of information and then augment with the audio stream? Visual models wise, we are a little surprised that the visually relevant contexts are not doing very well. But I think we have just sort of begun. We haven't really done anything like this before, just begun looking at that, and there's a lot more work to be done there. Fusion-wise, as Juergen pointed out, we have really considered very limited asynchrony here. There's a lot of different ways to actually constrain the asynchrony to be less than 3 states within a phone by actually manipulating explicitly the transition matrices. And we started looking at that during the workshop, but don't have any concrete results on that. And Herve started looking at some automatic estimation of stream confidences. And one of the things that clearly has shown a lot of benefit is doing unit-dependent weighting schemes. For the obvious reason that I said, only certain phones where this place of articulation is clearly visible, is it going to be useful to augment the audio stream with visual information. And I would like to, before I open it up for discussion, acknowledge a lot of people. Giri Iyengar from IBM has helped us quite a bit with some of the initial data settings, in particular looking at problems with our CNN data, which I haven't addressed at all. Sunil Sivanandan, in terms of, it was a major issue to get 80 gigabytes of data back and forth between IBM and here. Eric Helmuth spent a lot of time also annotating the data. Asela and Murat here have been very helpful in questions related to HTK. And Andreas Andreu and Eugenio helped us with some of the CNN data collection. Of course, CLSP staff, and special thanks to Amy, who in short notice yesterday afternoon helped us get us T-shirts that we're wearing today. Of course, Fred, Jelinek, Sanjeev, and Bill, I would like to say this, it was a very novel experience for me to be here with all these intellectually inspiring people. Even the undergraduates, June, Azad, and Jie, turned out to be extremely highly motivated. 2 graduate students, Herve and Dimitra, they are almost finished. So in spite of that, I think they were really motivated and spend a lot of time finishing experiments. With that, I will, anything else anybody would like to add before we open it up for questions? Okay. Yes.
At some point during the workshop, you invited someone to talk about human performance schemes with visual perceptions of Earth in noisy data. How do your performance schemes compare with human performance schemes?
I don't really remember the experiment that I have recall of actual numbers is the Quentin Sommerfeld experiment, where he went from 29% transcription accuracy at 0 dB or sub 0 dB SNRs to about 79% when the video was included with it. We are nowhere approaching those kinds of things. In fact, look at the lattice oracle error rate on the noisy data, which is about 27%, compared to the baseline that we had was about 45 odd. we have improved it to about 35. So there is still a lot of room for improvement right here. So I think those gains are more than 70, 80%. We are really here about 27% relative. Yes.
So, have you done an analysis yet to find out if adding the visual information helps the decision where the
No, I mean, systematic analysis of that sort should be done, but we haven't really done that. Yes. That's what it seems right here. Yes. I think in some ways makes sense because as I said in my very opening talk, although in theory both the visual and the audio realization should be dependent because they're being produced by the same underlying process, in terms of the way we actually measure them, the sensors, the sampling rates, the feature spaces, the distance metric, all are different. So we take what is dependent and make them pseudo-independent. So even the Bayesian conditional independence doesn't work. We are actually having exponent weights that add to these two decisions. Yes. Yeah.
Do you feel that maybe one of the problem is that the features that you that the visual features that you collect are kind of inadequate, and that you're parameterizing it, in a bed. And I mean, clearly, as I told you before, when I look, I have to do lip reading in many situations. For instance, in the theater, and so the information is there. You just haven't been able to extract it. I'm wondering whether this has to do either that you extract the wrong parameters or whether the head is moving. It would probably take a page out of what people do to cats at Chalapathy. I don't know if you've seen it. That they surgically attach a post so they don't allow the cat to move.
Yeah. Yeah.
Well, I mean, a controlled experiment.
No. Yeah, I think one way to think about that is to only get the what you call the visual region that corresponds to the mouth and nothing else, and do experiments on that. I believe you did, Iain, you did some experiments like that, or one of you?
And then there's all the ICP stuff with Blue Lips, where they promote you on live video. So you actually use makeup on somebody and get features this way. But so the trouble is you don't want to do that really. It's just extracting things out of images is very hard.
Yeah.
I mean, anything in the background, any scale, the variability is very massive.
Right. So here.
So it's the technique of extraction which you think is inadequate.
2D signals with anything you like as noise, as opposed to 1D signal, speech, or noise. It's really hard.
So it's, as I said, it's a combination of those, right? We are trying to look at the case where it's realistic. We have the face in a scene, and we want to extract the face, the mouth, and represent it. All these have
I just wonder, I mean, I don't know, Paul Scofield, who is a famous actor, he irritates me enormously because he speaks with his mouth open all the time. All right? Anthony Hopkins also. And I wonder whether the problem isn't that the speaker independence visually is much worse than the speaker independence in an audio way.
Right. I have the counter view, because I said the kinds of things that we need to capture from the video are much fewer. In other words, to distinguish between ma and na, it's sufficient to capture the mouth closure sometime during the duration of that phone versus na. But the point is, we may not be adequately doing that in a robust way just yet. That's the problem. Yeah.
The numbers you showed for the high data seem to be pretty close to the best numbers that you had. So why do you say that latency is better? Because that's the example of value.
Which one?
The numbers.
Yeah, no. The best numbers we have are based on late fusion, but Hilda actually comes close to that at this stage, and Hilda is actually early fusion because we are concatenating the features and doing a LDA on top of that. But the answer to that question was, what are the best numbers are based on, we are even beating that by doing decision fusion or late fusion.
But it's not really late fusion, it's kind of between early
Oh,
and
well, yeah. I mean, yeah, that's why I prefer to call it feature versus decision fusion rather than early and late. Because early and late have a lot of spectral variation in terms of what they mean. Yes? Yeah. No, yourself.
Yeah, I'm just.
You have to look at my right eye.
Okay, I'm
Yeah.
just a little confused about the strong emphasis on, in the results, on having this global weighting for the fusion of the two streams. I mean, if you look at the traditional conception of this problem, you have the supposedly complementary audio and visual, where something that's not easily distinguishable, the audio signal, can be helped by the visual signal and vice versa for different parts. So that would give you the phoneme level where you almost want this flip-flopping back and forth, where the weights are better for the visual, providing more information in one sense, and the audio in another for different phonemes. And with the global weight across the utterance, it seems that only says that we have a higher weight for audio, so the audio has more information, but then when it's purely audio, then the weight's lower because it's just degraded information, so you get more information from the visual. But it doesn't really seem to say much about how they're fusing together, or whether the early late is better, because it's just sort of saying comparatively how much information you're getting from each source, but you're really going to be getting, you want different information at different times depending on what the phoneme is. Of course, that's the problem, because if you're in the phoneme, you wouldn't have to do the recognition. It seems like you really want to work on the phoneme level, and that you're looking at these global weight. You have the clustering, but for the most part, it seems confusing. It's just looking at the separate streams and trying to rate them rather than trying to make them.
This is the best results we have are based on phone-dependent weighting. In fact, the clean result that Dimitra has is based on phone-dependent weighting, and Herve Glotin's results also, where he's beginning to approach how to actually weight it, not even at the phone level, but at the frame level, at every frame, based on, for instance, voicing. One of the things that happens when there is high noise is, again, based on Ken Grant's experiments, the confusions are between voiced and unvoiced signals. They get higher. So intuitively, if the voicing level in a phone is higher or across an utterance is higher, you would weight the audio more than the video, and vice versa. And this is the direction that Herve is proceeding in. But you're right. That makes sense. Okay. Michael. Yeah.
Just want to know what HIP Hilda was. I thought HIP was already.
Now, HIP Hilda is baseline. It's basically Hilda features if you decoded them as they are. So it's like IBM lattices generated using Hilda, rescored using Hilda models developed by HTK. So that's really the Hilda baseline. That's right. So, yes.
I'm curious about the asynchrony issue. Have you looked at when the lip motions and what you hear are put together? Have you looked at how much sort of anticipatory lip gesture there is? How much ahead of time you observe it, and the time when you observe it until the time you actually hear it, and whether your asynchronous model is capturing that?
Well, we haven't done it, but Christoph Bregler actually did measure based on mutual information, and he noticed that the lead of the visual could be up to 120 milliseconds compared to audio. So, did I say the name right? Or? Okay. So, but this changes obviously, and this is really at the onset. In continuous speech, you probably won't see anything. The other thing we noticed from an alignment point of view, I think Dimitra actually found that if you independently align using visual models and the audio models, she was observing about half a phone difference in alignments. So, and that's the reason to use these asynchronous models. But the asynchrony we are limiting. We are saying the asynchrony could be only within a phone. But that could be changed. This is what I mean by saying the synchronization points could be defined within the model. You could define that at syllable boundaries, or you could define that at word boundaries. Yeah. Does it answer your question? Yeah. Okay. Anything else? Okay, if not, let me. Eric Pettigen, incidentally, is the guy who I think is a person who did his PhD thesis on audiovisual speech recognition, the first guy to look at this problem, and he has since then been working at AT&T and Lucent Bell Labs, and now he's the chief scientist at his own company called Face-to-Face Animation, which is trying to get MPEG-4 based face animation systems. And he's going to talk about MPEG-4 based visual speech representations. Let me actually come back. You have,
Thank you, Chalapathy. As he mentioned, I've been working on this for a long time. It was actually the early 80s when I did my PhD thesis. Since that time, I've done a couple of versions of automatic lip reading systems. I've worked on high-definition television. But lately, I've been focused on audiovisual coding standards within MPEG, the latest being MPEG-4. And I chair the face and body animation ad hoc group in MPEG-4. And one thing led to another, and Lucent New Ventures Group decided to commercialize the face analysis work that I've been doing for most of the last 20 years, actually. So now we have a company. It started at the beginning of the year. Let me just have the thing speak for itself here. And show a few demos through the presentation here. They'll sort of speak for themselves.
Hi, I'm Heather, and I'm part of the Face-to-Face team. I would like to briefly explain the revolutionary technology that we have developed. I am being recorded on a consumer digital camera. The video will be processed through the Face-to-Face software, translated into facial animation parameters, or FAPs, and then applied to a face model on a typical animation software package, such as Softimage. What you are seeing is the untouched result. Now, the live face-to-face human being will tell you more.
Okay. So what we've done within MPEG over the last 3 or 4 years is to develop a set of parameters and object types for representing virtual humans. And I wanted to make sure that this standard represented visual speech very, very well, so that the parameters could be used for audiovisual speech recognition. And the pitch I'm going to make to you today is to use these parameters, because they're now part of an international standard for future work in audiovisual speech recognition, because this data will be floating around networks, wireless and the internet and otherwise, for years to come. Face animation is part of MPEG-4 version 1. Body animation is part of MPEG-4 version 2. Face animation parameters displace feature points from their neutral position. Body animation parameters are joint angles of the human skeleton. And both face and body animation parameters can be compressed to very, very low bit rates using a variety of compression techniques. Neutral face is defined with the head pointed straight ahead, the mouth closed, eyelids tangent to the iris. Tongue position is specified as well. We defined a set of feature points which are just sufficient to animate a face. The points that have that are filled in are subject to animation by animation parameters. The open circles simply define the shape of a neutral face. The animation parameters are normalized by expressing the deviations in terms of particular facial dimensions when you encode or when you extract the parameters, and when you apply them to a face model, you measure those same dimensions, with the exception of the head rotation parameters and the eyeball rotation parameters, which are Euler angles. So depending on the animation parameter we're talking about, it's expressed as either mouth width, mouth-nose spacing, eye-nose spacing, eye spacing, or iris diameter as appropriate. We've grouped the facial animation parameters for coding purposes, and because of the normalization, the animation parameters are independent of a particular face model. This allows private face models to be used, so you don't have to download a particular face model. It allows face models to be simple or complex. As an option, you can download face models using MPEG-4. It's not a requirement. So we've defined a whole set of containers in the decoder for holding vermal-based face models and various other kinds of data that allows complete predictability and fidelity of a particular animated face. I won't go into the compression algorithms much here because you probably don't care much about it, but the bottom line is that the bit rate for animating a whole face is less than 2 kilobits per second. So all the information we're dealing with for visual speech occupies essentially no bandwidth on a network. This allows you to decouple the acquisition of the visual features from the processing of those features. So your recognition engine could be in the network somewhere where the separated from the camera in a wireless terminal, for example. We've also defined a set of visemes and expressions. You can actually specify 2 visemes with a blending factor in a given frame, and 2 facial expressions with expression intensities for each of them respectively. But we haven't really defined exactly what these parameters mean or what the semantic is for these parameters. So at a first level, it really just hints to the decoder to allow a more precise interpretation of the low-level face animation parameters. However, you can download the definitions of the visemes and expressions in terms of low-level animation parameters if you desire, and this actually allows even lower bit rate coding of faces. So we defined a set of visemes which we wanted to be language independent, and these are basically target positions. They're not visemes perhaps in the sense that some people may think of them as correlates to phonemes. They're really target positions, and because you can specify 2 at a time in a given frame, with a blending factor, you can express co-articulation with the visemes. But there's still some room left to recommend a practice for these visemes based on future work. And we also have facial expressions. Again, these can be combined with the visemes. And these are the standard facial expressions from the psychology literature. Now, for lip reading with FAPs, you want the minimum set of FAPs. You want to reduce the number of parameters. If you assume symmetry, left-right symmetry of the face, there are 8 FAPs that describe the lips. The tongue FAPs are hard to acquire visually. Typically, you'd use the acoustic channel to estimate tongue movement. But the FAPs are normalized, so they're inherently independent of the speaker. And I think they represent the most compact visual data, especially when you go through the compression engine. So the lip FAPs in detail, in particular the inner lip FAPs, are as follows. You have the mouth corner feature points You have the upper and lower mid-lip feature points, and then 4 more points kind of halfway in between. The corners are animated horizontally and vertically. The mid points and the other 4 intermediate points are only animated vertically because their horizontal position is implicit. And then there's a lip protrusion fap for the upper and lower lip, which explicitly defines the protrusion of the center of the lip, whereas the rest of the lip protrusion is to be interpolated. Now, lip closure is explicitly defined as when the sum of the upper and lower lip flaps, a given pair of upper and lower lip flaps, equals 0, that means the lips are closed, no matter what the absolute position of the contact point is. So we've been very careful to maintain accurate representation of lip closure in the FAP domain. Now, Chalapathy mentioned lip protrusion. My feeling is that it's something that can be largely interpolated, estimated from a single view. I could be wrong about that, but the focus of my work is single view front lip extraction and face feature extraction. So the rules in MPEG say that if you only receive a certain set of FAPs, then the decoder has to interpolate the rest. So in the case of lip protrusion, I think the lip protrusion can be adequately estimated from a good set of horizontal or vertical deviation FAPs around the lips. So if you take away lip protrusion, that leaves you with a 6-channel information stream for lip reading. Now, the visemes, as I said, there are 14 of them, and there are 2 channels with a blending factor. And co-articulation can be represented with the blending factor. The visemes also go through the compression engine, so they don't really add significantly to the bit rate. But they can be used to label or annotate the visual stream on top of the low-level FAPs. This can also be very handy for lip reading if you're able to do some early recognition of lip shape. For example, if you have a labial dental viseme and you want to label that explicitly in the bit stream so as not to burden another part of the system, you have the option of doing that. As I said before, you can download definitions of visemes into the decoder in terms of low-level FAPs via the viseme def bit. When you set the bit, the associated FAPs for that frame get loaded into a table in the decoder. If the bit's not there, then those FAPs are looked up in the decoder. It's actually a form of vector quantization that can drop the bit rate for the FAP stream down to less than 1 kilobit per second. Of course, then we also have some paralingual FAPs: chin position, chin boss, cheek raise, cheek puff, head orientation, eyelids, eyebrows, the whole set of information above the nose. It's true that head gestures and gaze direction and eyebrow movement are really part of the speech signal as well, and at some point that information should be incorporated. But this is all part of one package, and these bits are going to be floating around networks very soon. So information's already there. You can take advantage of it as the research progresses. Now, as part of the MPEG rules, free reference software has to be available for every tool in MPEG. One piece of reference software is a little program called Wireface. Runs out of the box on an SGI machine, and it takes a FAP file, which is an ASCII file of animation data, and animates the face in real time with synchronized audio. It shows you exactly what's going on. The demo I showed at the beginning was driven strictly by a FAP file. And if anybody wants this program, just contact me and I'll give you the source code. You can do what you want with it. So in addition to lip reading, the MPEG-4 face animation specification enables a lot of other visual speech processing applications like text-to-speech. You can keep your text-to-speech engine in the server and output FAPS and then stream the FAPS and coded audio to your terminal, then reducing the burden on light clients. But you can also use the FAPS for enhanced computer-human interaction, especially if you're incorporating the gaze direction and just locating the person in general. So in conclusion, MPEG-4 is an international standard for true multimedia coding. It's actually been specified for third-generation wireless applications. It's been the cable television industry in the U.S. is wanting to use MPEG-4 for their next generation set-top box and digital television service. It provides very low bit rate coding and error resilience for internet and wireless applications. MPEG-4 face animation coding really is kind of a new form of entertainment at very low bit rates, and we'll start to see more and more streamed face and body animation parameters to browsers as time progresses. And there's some URLs for you to look at. Now, I did manage to get one of the audio visual test sequences from IBM, and I'll show you some processing of that. Now, the processing from face-to-face is MPEG-4 compliant, but MPEG does not specify encoders. So face analysis is sort of a free game at this point, and that's the main thing we're after, is providing robust analysis of faces, in particular the lips. But we do have a caveat that the nostrils have to be visible during the session, and we're after the inner lip contour. So we shot a person on video, turned that video into a frame sequence, extract the inner lip FAPS, and head rotation is estimated from the nostril position. And the bit rate for all the demos is less than 2 kilobits per second. The face models that we're showing here were all developed within Softimage. We have plugins for different animation packages, Softimage, Maya, and so forth. But eventually there will be MPEG-4 players out there embedded in browsers, which will take exactly the same stream. So let me just close with a few more demos here. Unfortunately, the projector is doing some strange things with the color on this. I'm not sure why.
Besides being a phenomenal typist, Albert Tengor developed a special technique for feeding new sheets of paper.
Somebody wants to see this after the talk on the laptop. It doesn't look like that on my machine. Model independence allows you to animate any face that you've applied the feature points to. So this is the same sequence I showed at the beginning applied on a totally different face geometry.
Hi, I'm Heather, and I'm part of the Face-to-Face team. I would like to briefly explain the revolutionary technology that we have developed. I am being recorded on a consumer digital camera. The video will be processed through the Face-to-Face software, translated into facial animation parameters, or FAPS, and then applied to a face model on a typical animation software package, such as Softimage.
Okay, enough of that. Now, what I showed initially was the inverse kinematic rigging that we use in our plugins to take the inner lip FAPS and deform the surrounding facial surface just from the inner lip FAPS. So we're not downloading any face models, we're just animating the faces from the head orientation and the inner lip movement. Everything else is interpolated. There's one more demo here.
You can't handle the truth. Son, we live in a world that has walls, and those walls need to be guarded by men with guns. And who's going to do it? You? I have a great responsibility, a greater responsibility than you can possibly fathom. You don't want the truth because deep down in places you don't talk about at parties, you want me on that wall. You need me on that wall.
Okay, that's it. Are there any questions? The what? Good question. All of the movement above the nose is synthesized. Eyes are blinking every 5 seconds. Eyelids are mapped to the lips, actually. I'm actually working on adding that to the system now, but that's not extracted from the video. Yeah.
How robust is the feature extraction, the extraction of those measurements with respect to different persons, different items, and different recording conditions?
It's very robust. I think we have the most robust system. That's why we're in business to do this. Yes.
So, a question that I'm sure has struck other people here also. You are currently synthesizing paths from video. You might also synthesize paths from an audio stream, having done speech recognition first. I'm curious whether you tried that and how good it looks.
You can certainly try to do that, and there are companies that animate faces from the audio channel, lip sync, for example. They don't go through the MPEG-4 standard, but they could. What you miss when you animate faces just from the audio is the head gestures, any of the facial expressions that manifest on the lips. And by going through a phoneme labeling process or some phonemic speech unit labeling process, and then to a viseme process, gives you a sort of robotic face animation. You get the same lip movement for a given phoneme, and so you don't get you don't have the visceral feeling that you're looking at sort of a human movement. It's a little more robotic. But processing the audio is actually complementary to what we're doing here. We may add that kind of processing at some point to get the tongue movement, for example, which we don't get out of the video right now. Yeah, that was this one. For some reason, the color is messed up. Want me to show it again? If you want to see it properly on the screen, I'll show it to you. Okay.
Make some remarks, so don't go away. I want to make remarks because I'm scheduled to make remarks, not that I know what to remark. So we are almost at an end of another successful workshop, and the success of these workshops doesn't even surprise me because we have them one after another after another. And what you observed here, namely the hard work and coherence of groups and team spirit and and the effort, etc. We see that every year. So I mean, I'd like to praise you as being exceptional, but I think that the computers went more smoothly than in the previous years. So I think we're learning something. Unless I'm mistaken. Anyway, during the steering committee meetings, there didn't seem to be any complaints. I think that I didn't register any complaints, period. So I don't know whether I am deaf to complaints or what's happening. We, of course, feel that this is a very good way to start research, and our experience, I don't know if you've seen on our web pages, we list, for instance, the papers that came out of work that started at the workshop, and that list is quite impressive, and I expect no less from you. And we will, of course, brag that, about your work, that it was facilitated by us. And I think that, we of course are very lucky in having these extraordinarily capable undergraduates, and I think this would be a great way to educate undergraduates or anybody in technical areas. The problem is that I don't know how many people I can attract from the senior researchers for this kind of business of education. Actually, we are planning, or we have submitted some proposals to NSF to create a center for, what do we call it? A natural communication with information systems, and NSF encourages outreach, and one of the main points of the outreach that we are offering is that we have this experience with these workshops. I think essentially this is the end of my remarks, but I think you ought to have an opportunity to tell us if you think, I mean, I would like to open the floor for anybody to make any remark about this workshop, or how we could improve it, or change it, or whatever. So, is there anyone who wants to? Yes.
I have heard from some people from MIT Media Lab and other places who are interested in actually hosting this workshop. They believe that it's nice to probably rotate this from university to university. What are your thoughts on that?
Well, my thoughts are naturally negative. And, you know, let them make their own workshops. You have to understand, I mean, I might as well disclose that we've got certain selfish motivation for having these workshops. The selfish motivation is that whatever computers we buy, we keep. And this, of course, supports our research for the rest of the year, and that's why our graduate students have excellent working conditions. And if we abandon the workshops, maybe we wouldn't have it. Otherwise, actually, just for you to understand, we have actually taken an enormous risk with this workshop, because at the last moment, NSF somehow misplaced the money and didn't have it, even though they promised. And this money was replaced by money from DARPA, and that money was taken from our own approved support. And presumably we will get this support in October, but those of you who know what the situation is DARPA is, you know that in fact DARPA somehow their budget has been cut, at least for tithes, where our money is supposed to come from. So, so we actually, this is a two-way street, and this year we're keeping our eyes, our fingers crossed to see whether we are not going to go down because we maintain the tradition of these workshops. Okay, so that's in answer to you. I think Mr. whatever his name is, what's his name? At the Media Lab, starts with N. Negroponte, you know, he after all has captured the imagination of the whole world by his salesmanship, and he ought to sell himself and not at our expense. Yes?
Fred, as I look at the various sort of technologies that are being advanced here, it becomes clear that a lot of it can be used for that huge task of foreign language learning. And I look forward to a project that exploits that whenever that's possible.
Well, as you know, we have these meetings at which we decide decide essentially as to what the subject of the tasks of the next workshops are, and we'll invite you again. And last time you made a proposal, and these proposals are kind of voted on democratically by the audience, and you know, that will be the wishes of the invitees, then that's what we're going to have. Any other remarks? Yes?
On the subject of matching Necropante in publicity, I'm just noticing certain facts about the workshop that have been very, you have the teams cloistered together, working on joint tasks against heroic odds, and I wonder if it wouldn't increase the publicity if someone were voted off of the island every week. Just a thought for next year.
With cameras in the dormitory.
Oh, yes.
They kind of lounge around. Okay. Anybody else? Well, okay, thank you very much for your hard work, and I expect to see you at the picnic, and hopefully we'll all enjoy ourselves.